Okay, what we're doing for most of the rest of this whole chapter is looking at these reactions from a viewpoint of concentration units, just like we had done in chapter 9. And then we're going to learn how to go from concentration units to calculate pH and vice versa. So let's do this. I'm just going to pull this in. Again, this is from your worksheet. This is section 3. And section 3 in your worksheet is referring to this equation we just did in section 2. And it says, how many moles of HCl is going to react if I'm using 32 milliliters of 0.1 molar sodium carbonate? Now, there's nothing new in this question. I could have put this on your last exam. You should have been able to do this. This is chapter 9 stuff. But just in case you're feeling a little bit foggy on this, I'm going to pull out our exam support materials and let's import our little roadmap. Sorry if you don't like the roadmap, because I'm just going to keep harping on this until you guys start to feel really good about it. All right. Okay. And what we see here with the roadmap, or what we don't see here with the roadmap, is this extra set of, we call it off-roading, right? That if I give you the volume of a solution that contains A or B, if I have moles and volume specifically in liters, I can get concentration in moles per liter. And that brackets means concentration. So if I'm given concentration like this, then I can go back and we can say, all right, they want moles of HCl and I gave them volume and concentration of Na2CO3. Do you think we could use, let's see, where are we on the roadmap? How can we use the roadmap to solve this question? We're given volume and concentration. Yeah. Actually, okay, so Erica says we're on molarity of A, and we can use molarity and volume to get us to moles, and that should help us convert to moles of the other thing. And remember, it's reflected, right? So I could either start here and go there, or start here and go there. And it doesn't technically matter, except that now we're in acids and bases. Guess what we could do? Just for fun. B can stand for base, and A can stand for acid. What do you think? It's like I planned it from the beginning of the semester. Okay. We'll do that. Okay, B stands for base. So we were given 32 milliliters, and hopefully you can see that's going to be, oh, we already determined. Yeah, that's the acid and this is the base. So we were given then the concentration of the base. It's 0.1 molar. We're given the volume. We have 32 milliliters. And this piece, we need the coefficients, which... Is this a balanced equation? It is a balanced equation. Oh, Sarah got it. It's a 1-to-1. So now we can just set this up dimensional analysis style. Na2CO3. Now wait, that capital M is useless. Oh, Sarah got it, because it means moles per liter. Let's replace that, because we don't want capital M. Okay, so we start with moles per liter, and then we're gonna stick, oh crap, I need liters, but I only have milliliters here. So let's see, 1 liter is gonna be 1,000 milliliters of anything, including the Na2CO3 solution. But we were given that we have 32 milliliters. Na2CO3 solution. Okay. So far, so good. We can cancel out liters, and we can cancel out milliliters. We can cancel out Na2CO3 solution. Okay, so now we have the number of moles of Na2CO3, which this tells me if I use the volume, I should be able to get there. Now the coefficients, which as Sarah noted, they are 1 to 1. Okay, so we have 1 mole of the HCl and every 1 mole of Na2CO3 that reacts according to this equation. That works. Moles of Na2CO3 cancel. Now we are at moles of HCl, and oh, then we stop. I'm like ready to keep on going. But no, we can stop here. We don't need to keep going. That's why you're supposed to always note what your target is before you get started so you don't just overshoot it. Okay, so 0.10 mole per liter divided by 1,000 milliliters in a liter multiplied by 32 milliliters times 1 divided by 1 gives me 0.0032 moles of HCl. How'd you guys feel about that? Are you guys like, hey, this is so easy. I prepared for this on the exam. I am on it. Do you want to do one more, or do you feel good about it? Good enough about it? Okay. Well, if you guys feel pretty good about this, and again, I hope you do feel good about this, because we just had a test on basically exactly this. Let's move on. Okay. Okay. That little p, the capital H, stands for the power of the hydrogen. And what it's doing is taking the log, actually the minus log of the hydrogen concentration. The reason that we use a log scale for pH is because the hydrogen concentration, depending on whether you're in an acid or a base, can vary widely. And we can predict this because we know what the K of water is. Okay? Now, water does this naturally, just a little bit, not a lot, but this is in equilibrium. Water will split up into some hydrogen ions and some hydroxide ions. This just happens naturally. This is supposed to be 2 arrows actually. Just like we saw back in chapter 7 on equilibrium, right? Now, does that mean that it splits up a lot? No, not really. It only splits up a tiny amount, but it's enough that we can actually measure it. And the K value for this equation, which in this case is called the K of W just because it's the K value for the water, is always equal to the products, H plus, multiplied together, divided by the reactants. But in this case, because it's a concentration, the concentration of water in water is just 1. So we can drop that, and we find that the K value of water, which is just the H plus times the OH minus, that is equal to 1 times 10 to the negative 14th. Which is to say, I think pretty obviously, that only a tiny amount of this happens. And really, mostly it's all just water, as you would expect. But it's measurable. And in pure water, of course, half of it's going to be H plus and half of it's going to be OH minus. So that's going to be, remember, these are multiplied, right? And so it's x times x is 1 times 10 to the negative 14th, or x squared is 1 times 10 to the negative 14th. So you wouldn't divide by 2 because it's not 2 times it's squared. You're going to take the square root to find that the H plus concentration in pure water is equal to the OH minus concentration in pure water, which is going to be equal to 1 times 10 raised to the negative 7th. So again, it's very small. There's like one little OH minus for every 10 million water molecules that there are, right? Very tiny. So you're looking at in pure water, again, that is 0.1, 2, 3, 4, 5, 6, 7 molarity is the concentration that's there. Now, of course, this is the K and it's at equilibrium. So if somebody sticks a bunch of acid in there, we know that as per Le Chatelier's principle, if you increase the amount of one thing, then it's going to get like offloaded this direction, which is going to decrease the amount of the other thing. The K value stays the same. So if I increase the H plus concentration, I'm actually going to decrease the OH minus concentration, such that when they're multiplied together, you always get 1 times 10 to the negative 14th. Does that make sense? So you end up with this scale, you could say, where we say I could be anywhere from like, say 0.1 molar H plus concentration all the way to, oh geez, let me use text. You end up with a scale where you could be anywhere from, say, like, you could even be at 1 molar H plus concentration all the way to 0.1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 molar H plus concentration, right? In a typical, not atypical, in a solution, aqueous solution with an acid or a base, this is kind of the range you're looking at, which is kind of enormous. And it's likewise, it's the same thing for my hydroxide, right? I could start with, if it's a very basic, 1 molar hydroxide, or I could, at the other end of it, if I had 1 molar H plus solution, then my hydroxide would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 molar OH minus, right? So this is our range, which is just enormous. I mean, we can't even, honestly, our brains can't wrap our minds around this huge scale of what we could be in terms of H plus and OH minus. So what we do is we take the log of it and we say, look, every time we multiply it by 10, we're only going to go up by 1. And that's where we get the power of the hydrogen. So you take, essentially, here's the equation that I would say you have to know, but you don't have to know because I'm going to give it to you on the test. The pH is equal to the negative sign of the log of the hydrogen ion. Okay, and the POH is the same thing. The little p means the same thing, means minus log, negative log of the OH minus ion. And I'll give that to you too. I won't give you this bit, although it might be helpful for you if you feel like memorizing it, that when you multiply the two together, you always get 1 times 10 to the negative 14th. But if you take the minus log of each side of this equation, you get the following, which I do give you. So the minus log of this side actually ends up giving you, because of the power of logs, which I'm not going to review, it gives you the pH plus the POH. And the minus log of 1 times 10 to the negative 14th is just 14. Right, so just how the two of these, when multiplied together, will always equal 1 times 10 to the negative 14th. The two of these, when added together, will always give you 14. And you've got the scale, which I had started to draw, and then I thought maybe I should talk to you guys a little bit more about it. Right, at the low end, at a pH of 1 or 0, let's say, this is very acidic. And at the high end, pH of 14, this is highly basic. And in the middle, pH of 7, this is neutral, right? Now the pH is just the power of the hydrogen. Why don't we use the POH? Oh, we could. We just only need one scale is the key. But if we wanted to, we would call this the pH. This is a POH of 14. And this would be a POH of 0. Right? Because the pH plus the POH has to equal 14. And in this case, the POH is 7. So you could use a pOH scale. You just only need one scale is kind of the reason that we don't use a pOH scale. We only use the pH. And this pH 7 comes from the fact that if you're neutral, the power of the hydrogen, the power of the hydroxide both, they're going to be 7 here. Do you guys see that? Okay. All right, so that's how you get to the pH. If you know the hydrogen or the hydroxide concentration, you can use this equation to find the pH or the pOH. And if you know one of them, you can calculate the other one. Okay. So for instance, let's say I want to know the pH of a solution. Here we go. What is the pH of a solution that contains 0.0150 molar of the H plus ion? And you would say, well, I know the H plus ion, and I'm just gonna plug it in here. So my pH is equal to the minus log of the H plus ion, which is equal to the minus log of the 0.0150, which is equal to what? Now, if you have your calculators, please pull this out and try it. Everybody's calculator is going to do this a little bit differently. For some of them, like this one I know, it wants me to put in the number and then hit the log button and then hit the negative sign. So it's like I'm going backwards. I put in 0.150 log negative. But for some of yours, you're going to want to put the negative sign and then the log and then put that in brackets and then hit enter. It's different depending on what calculator you're at. But practice it. You should get 1.8 as your pH. Is that what you got? Excellent. All right. Well, that was very straightforward because I specifically said you have H plus. But what if I said instead, what is the pH of a solution that contains 0.0125 molar HCl? Now what? You have to get to H plus ion from HCl. So this is the part where you, having memorized the strong acids, that's going to be helpful. Remember, the strong acids are ones which dissociate completely. HCl is one of them. So we can presume that because you've got, oh, here we go. We could write this out and say, look, my HCl dissociates completely. What I really have in solution is H plus and Cl minus. Well, ions in solution. The Q. Right. Behaves just like an ionic compound, even though it's not technically an ionic compound. It's very interesting. And we can say, well, look, if I started with 0.0125 moles in a liter here, then since every 1 mole of HCl gives me 1 mole of H plus, what I really am going to have is 0.0125 molar H plus and 0.0125 molar Cl minus in solution. Now I don't care about the chloride, I care about the H plus, but making this connection is important so we have the H to plug into the H plus. Do you guys follow what I did here? Okay, so because 1 mole of HCl produces 1 mole of H plus, then the concentration of HCl is basically the same as the concentration of H plus. Now this is like a reaction, right, with coefficients. And we can do this dimensional analysis style and say, look, I've got 0.0125 moles of HCl in every 1 liter of the HCl solution. And then we can look, we can see, okay, it's a 1-to-1. So for every 1 mole of HCl, that dissociates in solution, I'm going to get 1 mole of H plus ions. Therefore, as a result, my moles of HCl cancel, and it's the same solution. The HCl solution contains the H plus and the Cl minus, and so you'll find that your concentration of your strong acid is going to be the same as your concentration of your hydrogen ion as a result. Does that help? Okay. Now, we might not always do it as formally as this, but I want you to recognize that if you have a strong acid solution, concentration of that entire solution is the same as the concentration as your H plus, by definition of the fact that as a strong acid, it completely dissociates. This would not be true of a weak acid, only your strong acids, which is why you have to memorize, okay, these are my strong acids that I can treat like that, treat that way. Memorize those guys. Okay, so we take that first step. We recognize that the concentration of my HCl is the same as the concentration as my H plus, and now I'm just going to plug it in, right? The minus log of my 0.0125, or in my case, 0.0125, where's my cursor? Log and then minus gives me a pH of 1.9. You guys feel good about that? Okay, let's take it a step further. What if we want to know the solution? Go do this again. What, whoops, is the pH of a solution that contains 0.0105 molar sodium hydroxide? A little bit trickier. Okay. We could play the same game here that we did right here and say, okay, well, NaOH is going to dissociate into sodium ions. And hydroxide ions. Does it dissociate completely? Oh, Erica, you're like on top of it. Sarah, you guys know exactly what to do. Yeah, we're still going to play like we did up here. It's just at the end, as you are anticipating, we're going to have to find the pOH and then use that, subtract from 14 to get the pH. Okay, you guys have got this. All right, does it dissociate completely? Yes, it does, because this is an ionic compound and sodium is always soluble. So we can just say, all right, if I started with 0.0105 molar NaOH, what I really have is 0.0105 molar hydroxide. And then we can take, say, the minus log of the hydroxide, which is equal to 0.0105 log minus, okay, that's 1.97, 1.98, 1.98. And then we can say 14 minus the 1.98 should give me the pH. I'm pulling in this equation right here, right? So 14 minus the pOH gives me the pH. So 14 minus this guy, (12.02). Is that what you guys got? Well, here I was trying to make it all tricky, but you guys were not tricked. That is, yes, Erica, you're exactly right. It's a base. And you know it's a base because it has a hydroxide. So you can expect that it's going to have a basic pH. In fact, it's a really good self-check, right? If you go through this ho hum, and you're like, okay, my answer is 1.98, and you say, wait a second, I'm a base, I should have a pH in the basic range. What did I do wrong? That might remind you that you have to subtract it from 14. All right, that's a really good self-check. If I'm solving this for an acid, do I have a pH in the acid range? If I'm solving this for a base, do I have a pH in the basic range? Is that what I'm gonna get? How can I kind of predict that? Okay, let's do one more like this. Let's see. Okay, so the question is, what is the pH of a solution that contains 0.0038 molar of magnesium hydroxide? And yes, Erica, if you've got a base, then you can only calculate the power of the hydroxide directly from that. If you want the power of the hydrogen, you have to subtract it from 14. Okay, so before we answer this question, we have to just kind of make sure we can see what's going on here. MgOH2 is going to dissociate, and it's going to dissociate into magnesium ions and hydroxide ions. Is that right? Sarah, you're rushing ahead and you missed something. You're a clever girl and you have done everything right, but you missed one crucial piece of information. And that is when magnesium hydroxide dissociates, it produces 2 hydroxides. Oh man. Now what do we do? How do we account for that? Oh, it's really easy. Yeah, you're just going to multiply by 2. You got it. We're just going to say, oh, I've got 2 moles of hydroxide in every 1 mole of MgOH2. Pardon, 2 moles of hydroxide. And that means that our hydroxide concentration, because your moles of magnesium hydroxide cancel, and now you still have moles per liter here, is, that's right, 0.0076 molar hydroxide. And now we can proceed as per usual to minus log of the hydroxide is the P as the power of the hydroxide. We have to make sure that we're being specific about that, right? So we don't want to make a mistake. All right, and then we say, all right, they want the pH, not the POH. So we take that extra step and say 14 minus 2.12 gives me the pH, which is, 11.88 or 11.9. Excellent. Good. How do you guys feel about those? Okay. These really, they're not too tough. And I give you these equations, right? The hard part isn't putting it in equations. The hard part is kind of knowing which equation to use when, but I give you these equations. So you should be able to solve this. Okay, so let's look, and I'm just gonna actually pull this directly out of your worksheet here, because I think it's helpful. Oops, scroll down. Okay. Here I have an equation. I want to know what is the pH of the solution which reacts with this many moles of carbonate. Before I do this, I'm going to pull down there it is. There you are. Told you I'm going to keep using it whether you want it or not. Except now we have to expand upon it. We were off-roading a little, and now we're going to off-road a little more. Okay. If this is my acid, A for acid and B for base, then you know what? I want a clean one. Okay. If B is my base and A is my acid, then of course if I use volume I can find concentration. And since A is my acid, finding the concentration gives me the H+. My base, finding the volume concentration can give me the concentration of hydroxide. Okay, now taking it a step further, we can use the equation that the pH equals the minus log of the H+, and that's going to give me my pH. That's what we just did. And again, I give you the roadmap, but I don't go off-roading, and I give you the equations, so you just kind of have to know where to plug them in. And that just takes practice, right? But if I do this, I can find the pH. If I do this, I find the pOH. Of course, we don't really use a pOH scale, so chances are good that if you get the pOH, that eventually we're going to want to get the pH from that. And of course, the way to do that is to remember that the pH plus the pOH is equal to 14. Technically speaking, you can do the same thing down here. If I get the pH, of course you can find the pOH. It's kind of a weird thing to ask for, but sure, whatever. You can use that same guy. That still works. Okay, so now we've got the roadmap in place, and we can, I'm going to copy this and put it somewhere else too so that I can use it again later. Because I want to make this one, I want to use it. Okay, so they want to know the pH of a 590 ml HCl solution that reacts with this much CO3 2-. So where's the CO3 2- in this equation? The Na2CO3. Okay, perfect. Yes. So the Na2CO3, I want you guys to recognize that this is the CO3 2-, right? The sodium is not doing anything there. He's totally a spectator. Okay, so we have 0.0372 moles of this. And they tell us we've got 590 milliliters of this, and they want to know the pH. Okay. Erica asked a question. She says, will you ask the power hydroxide on the test to be mean? And the answer is, I'll ask the power hydroxide on the test. I don't know if that's being mean or not, but it just as a way to help probe your understanding, I will. I could ask it for a base, and I could potentially ask it for an acid, although that's kind of weird. It's just more academic, but it wouldn't hurt. Okay, Sarah says, why don't we use sodium hydrogen carbonate? Okay, so again, if you're looking carefully at the way this is worded, we're saying we have this HCl solution reacts with this guy. So we know that both of these have to be reactants, right? So technically, yeah, there is a CO3 2- over here, but that's not what it's being reacted with. Yeah, excellent question. All right, so we have kind of looked at this equation and we see what we've got here. Let's orient ourselves on the roadmap. And again, we're going to say A stands for acid. It's like I planned it from the beginning of the semester, knowing that someday you'd be stuck with this kind of question, right? And B stands for base. So I'm asking, excuse me. So they're asking for the pH of is this the acid or the base? Yes, you guys are perfectly right. The sodium carbonate is the base. The HCl is the acid. So they're asking for the pH of the acid. So this is my target right here, the pH of that acid solution. This is where I am going. Target. Okay. And they did give me the volume right here. I've got 590 milliliters. Just plug that in. They did give me the moles of the base up here. Okay. Gave me this little guy here, 0.0372 moles. Okay. So when you're given several different pieces of information, and you might say, okay, well, where do I start? Where do I end? You're always going to start at the farthest out position, right? You're going to say, I have this piece here, but that's closer to my target. So I'm going to start here. It's further out, and I'm going to converge on this piece, and then together we're going to use that to solve this piece. Does that make sense? Okay. So starting from moles of B, looks like I'm going to need to go to moles of A. So help me out. What do I do with that? It is. Good job. Nicole recognizes. She's like, this is a one-to-one relationship. I still recommend, strongly recommend, that you do this dimensional analysis, because it's not always going to be one-to-one. And on the test, I might not give you one that's one-to-one because I'm kind of rude like that, right? You guys know me. You don't have to worry about the any at all. Nope. In fact, you can just remove that. Yeah, and it probably won't be balanced either. No, you're not wrong. And I'll probably give you the names instead of giving you the formula, right? Right? Probably give you an equation that's not balanced using the names. And it's not going to be one-to-one. See, if you're just prepared for that eventuality, then you won't be disappointed. And instead, you'll just be excited and be like, I got this. I'm so smart. Okay. So this tells us, the roadmap says, we start from the moles of B, we use the coefficients, we should get to the moles of A, which we did. Excellent. And remember that the moles of HCl is the same as the moles of H+, so I don't really need to worry about I don't need to worry about that. It's the same as the moles of H+. I shouldn't use that kind of bracket. Okay. So we got moles of acid. Now it says, hey, you can use that volume I was given to find the concentration of the acid. Okay. So here we go. I am going to need more room. Good observation. Let's just slide this guy over. Right, okay, I'm going to need liters to milliliters because this is milliliters and my unit of concentration has got to be liters on the bottom, right? So, okay, 1,000 milliliters and every 1 liter, that gives me liters on the bottom. And then I need to cancel out milliliters, so I'm going to just put 590 milliliters on the bottom. Don't need anything on the top. This was just given by itself, right? And I get to put those units where I want them because I'm the boss of them. Okay, so my milliliters cancel, and at this point I've got moles per liter of the HCl. And at this point, I've got to get off my dimensional analysis train because the next step is a formula. Just going to kind of fluidly move between the two. Okay, so 0.0372 times 1 divided by 1 multiplied by 1,000 divided by 590. That gives me a concentration of 0.0631. Molar HCl solution, which of course is the same thing as saying 0.0631 molar H+ solution. Okay, and now we're just going to plug it into this guy, the minus log of that. Okay, the log minus of that gives me pH of 1.2. Perfect. You got it. Okay, so what I want you to see here is this looks terrible. Really, if you were looking at it from the outside, if like you from 4 months ago looked at this, you'd be like, what is going on? But the fact is, we have been practicing this kind of stuff for the last, 6 weeks, and adding in this little leg on concentration units for the last test, no big deal. And all I've got left to add in are these equations, which I give you, right? And we can solve these problems. Just a natural extension of the types of problems we've already been solving, so that we can report our answer as a pH on the pH scale. That's all we're doing here. How do you feel about that? Should we do another one? Or do you feel like, no, I got these. We're good. Okay, we're gonna do another one. All right, from the same worksheet, number 3, same kind of story. Let's pull this down here. See, I knew that I was gonna need another one of these. That's why I stuck it here. In fact, I'm probably gonna need it again in a minute, so I'm just gonna copy and paste this down here, just in case. Okay. What is the pH of a 1.25 liters lithium hydroxide solution which neutralizes 2.32 liters of an HBr solution with a concentration of 0.0678 molar? Whoa. Sarah's got a great question. Am I going to give you a new roadmap that's got this stuff updated? And the answer is, Erica said, you've got to memorize it. I'm not going to give it to you. I give you all the pieces, right? I give you all of these equations. This piece you'll have to remember to get there, right? But you guys can do this. Of course, this side of off-roading is only good for solutions, and then this section of off-roading is really only applicable to acids and bases. That's not to mention the off-roading that could go on over here that we did with gases, right? Using PV equals nRT, we can take it over here. We're not doing that today though, so we're gonna ignore that. Yep. Okay, so let's orient ourselves. Always a good idea. Pull this down. We've got 1.25 liters of lithium hydroxide. We've got 2.32 liters of HBr. And that solution has a concentration of 0.0678 molarity. And they want to know what is the pH of that guy. Okay, so remembering that A stands for acid and B stands for base, then let's identify which of these is my acid and which of these is my base. Good, the HBr is your acid. It's got the hydrogen to donate. Your lithium hydroxide is the base. Okay, so just as a reminder, HCl is the acid. IOH is the base. Okay. And they told us the volume of my HCl solution, it's 2.32 liters. And they told us the concentration, that's 0.0678 molarity. Okay. And they gave me the volume of the base, which is 1.25 liters. And they want the pH of the base. So that's actually going to be all the way out here. This is my target. It gave me 3 different pieces. And again, we're going to just start from the piece that's the furthest, which is this guy. I'm going to start here. We're going to go this way, this way, this way. This is my planned route. And everything in this section is going to be dimensional analysis, and then I'm going to get off the dimensional analysis train and jump on doing some algebra to get to the end. So help me out. Where am I going to start with my dimensional analysis? (0.0678 moles HBr in every 1 liter of that HBr solution. How big is it? Okay. Perfect. And the roadmap tells me use the volume to get to moles. Okay, so we're going to multiply that by 2.32 liters of the HBr solution. Good. My liters of HBr solution cancel. And we're left with moles of HBr, which is just where we're supposed to be if we're following the roadmap. What do we do next? Right, we've got to use the coefficients of the balanced equation. They gave me an equation, is it balanced? Are those the right coefficients? Yes, it is balanced. Those are the correct coefficients. Okay, so 1 mole of LiOH reacts with 1 mole of HBr. My moles of HBr cancel. Excellent. Okay, so now I've got moles of LiOH. That's my moles of my base, which is exactly what it should have been. And now this is telling me to use my liters here to find the concentration. All right, so I'm going to put 1.25 liters of my LiOH solution on the bottom, and that's going to give me moles per liter of LiOH solution here. And this is where I've got to get off my little train here. Okay, moles per liter. So we've got 0.0678, multiplied that by 2.32, divide by 1.25, and I get a 0.126 molar LiOH solution. Is that what you guys got? Okay. Now, I'm going to do this next part in my head, but if you want, you can always write it out and say, okay, LiOH dissociates to form Li and OH. Just verify that it's a 1-to-1 there. That should be done. Okay. So, but I'm just basically going to take that extra step and say that's the same as 0.126 molar hydroxide. And then I'm going to say, all right, the minus log of the OH minus solution is equal to the minus log of 0.126, which should be equal to my P of the OH, since that is my OH, right? So the log of that, the negative of that, gives me 0.9. Okay. So that got me from there to there. And then this reminds me, oh, you're not done. Subtract that from 14 to get the pH. Okay. So 14 minus 0.9 gives me 13.1. That's the pH. What do you guys think? One more? Sarah asks, do we need to specify that it's the pH of the LiOH? No, because they're asking what the pH of the LiOH is. So it should be, that should be included there. It's okay to just say this is the pH. In fact, the pH doesn't really have any units, so you could just answer 13.1 is the pH of the solution. Okay, let's do one more and then I can let you go for the day, okay? Is that fair? Unless you feel like you're all good and you don't want one more. One more. Okay, here is our last one. So we want to know what's the pH of this 0.495 liter HNO3 solution, which reacts with 0.267 grams of NH3. Oh, fun. Okay, so just to identify which of these is my acid and which of these is my base. Good, the HNO3 is the acid in this case. This is my base, which is the NH3. Good. All right, and they are telling us that we have 0.495 liters of this guy, and we have 0.0267 grams of that guy. Okay, fun. And they want to know the pH. All right. If we orient ourselves here, they want to know the pH of the acid. So this is our target. And to help us, they gave us the volume, 0.495 liters. And then they gave us the grams at the base. So we're like all the way over here. That's okay. We're going to start with 0.0267 grams of NH3. And then calculated, we have 1 nitrogen plus 3 hydrogens, give you 17.034 grams per mole. We're going to put that on the bottom. So 1 mole NH3, 17.034 grams NH3. Good. Grams cancel. Now we're at the moles. We just need the coefficients, which is 1 to 1. We'll plug that in. 1 mole of HNO3 for every 1 mole of NH3. There we go. That brings us to moles of the acid. Then we're going to use our volume to get to concentration. 0.495 liters of my NH3 solution. That gives me concentration of NH3, of my HNO3 solution. Okay, so 0.0267 divided by 17.034 divided by 0.495 gives me 0.00317 HNO3 solution. And because this is a strong acid, dissociates completely. We know every 1 mole of HNO3 is going to give me 1 mole of H+. So that gives me 0.00317 molar H+ solution. And then we can plug that into my pH equals the minus log of that H+. So the minus log of that 0.00317 log minus 2.5. Sarah's exactly right. Well done. Okay. Have a great weekend, guys. Have a great Thanksgiving. We'll see you Tuesday.